Log on, tune in, find out. Another good idea from Cambridge.
Thanks everyone. I'm Dan Pagendam from the CSIRO, the Division of Mathematics, Informatics and Statistics, where I'm a postdoctoral fellow. And I'll be talking to you today about some research that I did during my PhD, which I finished last year, which is on optimal experimental design for stochastic population models. Okay, so the sorts of models I'll be talking about today are continuous time Markov chains, similar to birth-death processes, which I'm sure most people have encountered before. These are popular models in population biology, particularly ecology, epidemiology. And I'm going to be looking at a question which is sort of a common theme in some of the other talks today, which is at what times do you observe such processes if you can only observe discretely? So we're going to be looking at mainly de-optimal designs, I guess, but I'll be talking mostly about ways to evaluate the information matrix. So why are these processes interesting and useful? Well, they're used, as I said, they're continuous time Markov chains, popular in population biology and epidemiology. Markov population processes, the title of this slide, are generalizations of birth and death processes, and they're useful models because they allow us to calculate quantities such as the expected time until extinction of a population or the probability of eradicating a disease, say, over a certain time horizon. But in order to calculate such things, we need to be able to estimate parameters, and in the sorts of fields that we're talking about here, these are typically transmission and recovery rates in epidemiology, or in population biology, we're looking at things like birth, death rates, immigration and emigration rates. So, continuous time Markov chains are formulated by specifying a set of transition rates, which we denote Qij. Qij represents the rate at which we transition from a state I to another state j in a state space denoted here S. And for processes with a finite state space, we structure these into a matrix which we call a Q matrix, whose ijth entry is this transition rate from state I to state j, and whose diagonal entries represent the total or the negative of the total rate out of state I. And birth and death processes are simple examples of such processes where we only allow transitions from, say, state I to I plus 1 and death from I to I minus 1. So matrix is very sparse, tri-diagonal matrix in the case of a birth and death process. Now the transition probabilities of a continuous time Markov chain, such as the ones I'm discussing today, we have the Kolmogorov forward equations, which dictate the way in which the transition probabilities evolve with time. So P contains the probability of occupying each state in our process at time t, and given our Q matrix and some initial vector or vector of initial conditions, probabilities of occupying states at time 0, we have the solution Pt equals P naught, and then multiplied by the matrix exponential of Q times T. Now, Markov population processes, as I mentioned, they're a generalization of birth and death processes into higher dimensions. They were originally introduced by Kingman in 1969, and we're now dealing with continuous time Markov chains where our states are vectors, and we only allow transitions from a vector n to a vector m, where we either increment one of the dimensions of our vector by 1, which corresponds to an arrival at dimension I, or we decrement one of the dimensions of our vector, which corresponds to a departure, or we allow a transfer from one dimension to another dimension of our state vector, which is a transfer, I suppose. The main challenge in this type of work is computing the Fisher information matrix. There's really 3 scenarios, and I'm going to try and discuss them all in my available time that we run up against. There's some very simple models. We can calculate the Fisher information analytically. This is definitely not common, and even for some one-parameter models, we can't do it. For some small systems, we can compute it exactly numerically, but for many larger systems, we have to resort to approximations, and this is something I think Gavin Gibson will also be talking about on Thursday, and I'll be talking about the use of Gaussian diffusion approximations. So the basic setup, if we were interested in, say, d-optimal designs, the basic setup of the experiments that I'll be talking about is we have some interval of time, 0 to t max, in which we can schedule, say, little n observations, and we want to schedule these observations in such a way that we maximize the determinant of the information matrix. Now, the first paper to look at this sort of problem was a paper in 1983 by Gerhard Becker and Gertz Kirsting in the Advances in Applied Probability. And they looked at a model that goes by many names: the simple birth process, the linear birth process, the Yule process. And it's really the Markov process analog of exponential growth on the non-negative integers. So the transition rates of this process is a pure birth process, so it only allows growth in the population size. So the rate at which the process goes from having n individuals to n plus 1 individuals is equal to lambda times n, lambda here representing a per capita birth rate. And we can solve the Kolmogorov forward equations to obtain the transition probabilities of the process. And so writing out the likelihood and the Fisher information is very simple. So Becker and Kirsting were able to show that for the simple birth process, the gaps between observation times, this is for lambda equals 1, but the same recurrence relation applies. There's this recurrence relation between the gaps between the times, governed by these two functions, phi1 and phi2, and that the last observation should always be taken at the last possible moment, so equal to t max. So the idea is this: so we know how many individuals we start with, and we, in this example, have 3 opportunities to observe the process. It's a static design, so we decide from the outset when we're going to observe, and these would be the times at which observations would occur if we had 5 units of time in which to take our observations. A related model, which I looked at during my PhD, is the simple death process, or linear death process, which is the Markov process analog of exponential decay on the non-negative integers. Transition rates, we now have a pure death process, so we go from having m individuals to m minus 1 individuals at rate mu times m. So mu here is now a per capita death rate. But we also have a more interesting feature, which is we now have an absorbing state at 0. So we're losing individuals with time, and once the population is extinct, there's no more information to be gathered. Now again, we can write out the transition probabilities of this process, and we can get the Fisher information matrix. Interestingly, this process has had some history, I guess, in various guises. The design sort of appeared in Chernoff's paper in 1953 in the context of taking one observation from a population of size 1 individual. And also more recently with Alex Cook, Gavin Gibson and Chris Gilligan in 2008, who looked at it from a Bayesian optimal design perspective. Myself and Phil Pollett showed last year that the optimal observation times also satisfy a recurrence relation involving the gaps between the observation times and a sequence of numbers represented here qi, and the primary branch of the lambda w function w0 here. And this is what designs look like for the death process. Again, we observe, we know how many individuals we start with, and we can take 3 observations. We can take them here, here, and here, and you can see that we don't always use, for obvious reasons, the full amount of time available. We can also start to look at things like how much information do we lose when we observe discretely. So in this graph, you can ignore the time, unconstrained, constrained business, but each curve here shows the ratio of the Fisher information under our optimal design relative to the information that would be obtained if we observed the process continuously, by which I mean we would observe all of the exponential holding times for the entire process. So the curve labelled 1 represents if we just took one observation. You can see we do pretty well. With one observation, the worst we can do under an optimal scheme is to retain 65% roughly of the information. For 2, the worst you can do is 85%. So you actually get quite a lot of information without observing continuously. As a second example, I'll discuss where we can compute the information matrix numerically exactly, and I'll talk about designs for metapopulation. So a metapopulation is a population network or a population occupying geographically distinct patches of habitat. And I couldn't come all the way from Australia without showing some funny critters. So we've got 3 species that live in metapopulations. On the left-hand side, we've got the bilby. In the middle, we've got the flying fox. And on the right, the koala, all of which prove God has a sense of humour. So the idea is here that we have various patches of habitat, and that individuals can transition between these patches of habitat. They migrate between them. And ecologists are interested in understanding, I guess, the dynamics of how these individuals move. And a popular model that they like to use for modelling these transition rates is the following. So these are the rates at which an individual moves from patch I to patch J, and we have 3 parameters: mu, delta, and theta. Dij here represents the pairwise distances between patches of habitat. And the experimental design now is we are going to tag individuals with GPS or radio tags and observe the locations of individuals at discrete points in time. And we're going to assume also that tagged individuals behave independently of one another, so that we would apply the same design to all of the individuals that we tag. Okay, so how could we go about getting the information matrix for this sort of experiment? Well, one approach is to take the Kolmogorov forward equations and to differentiate with respect to the parameters, and then to form this extended Q matrix, which has the original Q matrix along the diagonals and various derivatives elsewhere. We can then get the necessary ingredients that we need for calculating the entries of the Fisher information matrix by using the matrix exponential of this new Q matrix multiplied by time, and using a vector of initial conditions, which is essentially just the same starting state vector, which I've called y0 here, and a bunch of trailing zeros, which are put into this vector w star. There's a very efficient procedure for doing this, for computing the matrix exponentials. So a tool called ExpoKit, which was developed by Roger Sidge at the University of Queensland in 1998. And it's developed really for application with continuous time Markov chains, particularly those that have sparse Q matrices, such as we have here. So once we've got those ingredients, calculating the entries of the Fisher information matrix is actually very simple. And we can start to look at really interesting things. So, for example, once we've determined the optimal times at which to observe, we can work out the optimal times at which to observe the individual, constrained to starting, say, in different initial habitat patches. So we can start to see the effect of the initial conditions of our process as part of the design. And it turns out in some cases to be quite important, others not so much. For this particular example with 9 patches, you can see that you can get, well, you can lose roughly about 30% in terms of de-efficiency by starting in the wrong patch initially. Okay, and finally I'll mention a compartmental epidemic model as an example of a process where we can do neither of the previous two, take neither of the previous two routes. So we can't get our information matrix analytically, and we have a system that's too large and prohibits us simply using matrix exponentials to compute it. So we have to rely on approximations. And the model I'll mention is a model which has a great name. We call it the CSIRO epidemic. And it's an SIR model where we introduce K infectious classes. So one of the big criticisms, I guess, of using continuous time Markov chains is that the amount of time an individual spends in each state is exponentially distributed. And people don't like that, particularly when the amount of time you spend with the cold, say, definitely doesn't have an exponential distribution. So one way to get around this is to sort of tweak the model a little bit. So we now have K infectious classes, so that the amount of, or you could have as many as you like, but the idea is that you can come up with processes where the amount of time spent in a particular state, say infected, has a phase type distribution rather than an exponential distribution. So the CSIRO model, these compartmental epidemic models, you can think of them a little bit like the metapopulation example. We have now, though, a linear network, so an individual will pass through a linear network. But if we have multiple individuals and they don't behave independently of one another, we end up with a Q matrix that can be quite large. Okay, so this is the problem. So we have a Markov population process that has vector states. S here represents the number of individuals that are susceptible and do not have disease. And I1 through to IK represent the numbers of individuals in our various stages of infection. Okay, so the rate at which an individual transitions from susceptible to the first infectious state is equal to beta, a transmission rate, multiplied by the number of susceptible individuals, multiplied by the total number of infected individuals, divided by capital N, which is the total number of individuals in our population. And then we're going to use constant rates of progression through the infectious classes. So the rate at which an individual goes from I1, say, to I2 is lambda times the number of individuals in that class. Sorry, not lambda, gamma, my mistake. Okay, so the amount of time an individual spends in this example, the amount of time an individual spends in the infectious state is gamma distributed. And this is an example of what trajectories of a CSIRO epidemic might look like. You can see the number of susceptible individuals behaves like a death process. It just dies away, whilst the number of infected individuals sort of peaks and then falls away as individuals recover and, I guess, have immunity to the disease. As I mentioned, the transition probabilities can't be calculated as analytical expressions. And for large N, so for large total population sizes, calculating these transition probabilities and derivatives with expo kits computationally expensive. So we rely on approximations, in particular Gaussian diffusion approximations, which can be used for a very large class of models called density-dependent Markov processes. So density-dependent Markov process is one where the transition rates can be factorized, so they're equal to some index parameter or scaling parameter capital N multiplied by a function which is solely a function of the population densities. So here for our CSIRO model, M was the vector of the numbers of individuals in each state divided by capital N, we get the population densities. As I said, capital N is a scaling parameter. Typically it's the number of individuals in the population. And if YT denotes our density-dependent Markov process, then we call X of t, which is just Y of t on N, the density process. And we rely on two theorems that were proved by Thomas Kurtz in 1970 and 1971. He proved a functional law of large numbers for density-dependent Markov processes that state that as our system size grows, so as n, big N, goes to infinity, the trajectories of the density process converge in probability over finite time intervals to unique deterministic trajectory, little x of t. And he also proved a functional central limit law for density-dependent Markov processes that says that as the scaling parameter gets large, the scaled fluctuations of the density process about that deterministic trajectory converge weakly to a Gaussian diffusion whose covariance structure can be calculated. This approximation works very well for population sizes greater than about 100. So just to illustrate, I have to apologise for the y-axis on this graph. It shouldn't say number of infected individuals, it should say proportion. But we've got in red here is the deterministic trajectory. You can see up the top we've got capital N, total number of individuals, and as we allow that to get larger, you can see us converging to the deterministic trajectory. So what this allows us to do is to approximate our transition densities essentially using a Gaussian kernel and essentially treat our discrete state process as a diffusion process, which is and a Gaussian process at that. So the entries of the Fisher information matrix are now easy to compute, and we can use our optimization routine of choice to come up with an optimal design. For my PhD work, I used a method called the cross-entropy method for no particular reason other than that one of the students in the office next door was studying the cross-entropy method, so it seemed like a fun optimization routine to use. So I'll sort of explain how it works. If we were to, say, want to find a design, we've got 0 to 10 as our time interval in which to find observation times, and we're going to look at 4 observation times. We start off with a beta density on each of those observation times, and we initiate them as being uniform. And we generate, say, 1,000 designs. We pick the top 10%, and we use those top 10% to re-estimate the parameters of the beta densities. And with each iteration of the method, the mean of those densities converges towards the optimal observation time. Interestingly as well, the variance of those distributions tends to tell us something about the sensitivity, I guess, of the timing of those observations. So we tend to have a little bit more leeway with maybe this one than we do with the fourth one. Okay. So one of the nice things about our diffusion approximation, as I said, it allows us to work not only with exponential holding times, but we can also incorporate more general phase type distributions as the time spent in particular states. We can also deal well with unobserved states. So in the work I've done with the Zika epidemic, we've assumed that for obvious reasons, we can't observe which of our K states, K infectious states, an individual is in. All we can observe is that an individual is infected. And we can also look at the situation where we can't actually determine whether an individual is susceptible or recovered. So the only thing we can observe is how many individuals are actually infected at a particular time. And as with the metapopulation example, we can look at optimal initial conditions as well for how many infected individuals should we introduce into a population of infected individuals if we want to get the most information out of it. And it turns out there is an optimal number. It's not too little, it's not too big, it's just right. I should be in advertising. So you can see here that the optimal initial conditions for this example were here and here, but we do not observe the number of susceptibles over time. We're just taking 3 observations of the total number of infected individuals. Okay, and that's it. I'd like to thank my collaborators, Phil Pollitt, who supervised my PhD at the University of Queensland, and also to Joshua Ross at the University of Adelaide, with whom I'm working on the design for metapopulations, and who I worked on the diffusion approximation for the Zika model while he was at King's College here. Thanks.
We have time for discussion. mentioned about high computational burden related with determining those designs. Could you give some more details? What is the limit?
Yeah, okay. Well, I think it really depends what platform you're working in. A lot of my collaborators are using MATLAB, which sort of limits us. I mean, the ExpertKit implementation in MATLAB, whilst very good, probably realistically only limits us to in the order of a couple of hundred, like a couple of hundred by a couple of hundred Q matrix. But it's also available in Fortran, which is something I keep meaning to look at as well. Maybe interfacing that with R or something like that. In which case, I think you probably get up to maybe 1,000 or something. But that's just my gut feeling. Yeah.
Henry?
And with your observations, you're only really observing the state, right? What happens if you observe the transitions themselves?
Right.
I mean, does a radical gain in information? Have you done any kind of mathematics on that?
I haven't done much, but I can tell you, well, I mean, in terms of the single parameter models, there doesn't tend to be much benefit. You can get a lot of the information by observing, taking a couple of discrete observations. But as soon as you move into multi-dimensional models, observing the holding times means, somebody spoke this morning about the correlation between the parameters, basically. So that vanishes, obviously, if you're observing all of the holding times. You no longer run into having dependence between parameters, I guess. That's probably the main advantage. But yeah, I think in multidimensional models it would tend to have a much bigger impact than it does in the single parameter models.
Can I have nobody else has got an additional one? If you some of these if you have feedback, have you? Quite often it's much simpler if you have like one absorbing state. Everybody's going to die eventually. Everybody ends up in an absorbing state.
Yep.
But if you have feedback, does that, in my experience, that makes a radical difference to everything? Is that?
Not really sure. Feedback in what?
Well, you can get ill. You can be ill, and you can be well. So you can go backwards between.
Oh, I see. Yeah. So there's a model, the SIS epidemic. Is another one that I've looked at. So that's also goes under the guise of the stochastic logistic model. So it's basically a logistic type model. So that's quite an interesting model as well. So you see sort of an initial growth phase, and then something that starts to behave like an Ornstein-Uhlenbeck process, a mean reverting process. And that's quite interesting because in that type of model, the initial phase really, you made a comment earlier about, reparameterizing to get, parameters that are of interest in the model, I suppose, and you can reparameterize that so that you end up with an initial drift parameter and a location parameter for where the stable equilibrium is. And in that sort of model, you really come out with this idea that if you miss sampling in this initial growth phase, you're stuffed. There's two phases in the model. If you don't sample early enough here, your experiment's basically a failure. So yeah, that sort of thing is quite interesting as well.
Thank you very much.